let's pull an example from your homework. So I've made these homework problems. So this is like all your homework here. The ones I'm looking at here start with 7, I think it's 7, 8, 9, 10. And actually 11, 12, 13 are in the same family. But for this lecture, I'm only assigning 7, 8, 9, 10. And I've set up these homework problems so that each one shows you a different situation. So if you go to actually plot, so I'll discuss this in a second. But if you just, for each problem, go and plot and try to understand the trajectories in the phase plane, I think it will help you. Each one will have something different to offer. Okay, so let's just try this one. So we've got a differential equation system, and we need to find the general solution. There are no answer blanks to fill in, but you have to do it because without the general solution, you'll probably not be able to find a solution that satisfies certain initial conditions. And then the second part, I had this made sense the last time I taught this course because I was able to do exams that quarter. And so I could, test people to see if they really were, without a computer, sketching these things to get the right pictures. But this quarter does not make sense to have tests. So this is like all up to you, just depending on what value you want to get out of the problem. You can, without or with a computer, I think it would be great if you did it with a computer also. Just look at the trajectories in the phase plane. And you can do this with any plotting tool, basically. Once you get your trajectories, anything that can make parametric plots, Desmos or whatever, will do it. But as usual, I will show you how to do it with Mathematica. Okay, then we get a solution that satisfies certain initial conditions. And then we want to classify 0, 0 as a critical point. So there are a bunch of options here, and there are some that you don't recognize now and some that you will not recognize even at the end of this lecture. But don't worry about it. You will know them all probably by the end of the week or maybe early next week. So some of them will be explained later on. But the idea here, well, how about I get into it and then I'll explain the idea here when I get there. So let me copy over this differential equation system. Okay, here it is, two unknown functions, x of t, y of t. This is linear, homogeneous, constant coefficients. And what we can do is package together x of t and y of t like this in one vector valued function, if you want to call it that. So like a function with two components. Then this whole thing can be written like this. X with a vector symbol prime, so x prime y prime equals 8 minus 6, 9 minus 7, all times x, y, or let me write it like this. Like that. And then let's just call this A, this capital A. And then how do we get the general solution? Well, the general solution will be a linear combination of two linearly independent particular solutions. So just find two linearly independent solutions. That's our goal. Okay, how to do that? Well, solve the eigenvalue problem for this matrix. So let's start there. Okay, so we need to solve the eigenvalue problem for this matrix A equals these coefficients that are sitting here. So let's start by finding eigenvalues. So 0 equals this thing, that will give us the characteristic polynomial. Okay, and then I expanded this out and then I collected terms and it simplified down to this. So now I need to factor this polynomial. And I'm not seeing very clearly how to factor it, so I'm going to use the quadratic formula. So lambda equals 1 plus minus square root 1 minus 4 times 1 times negative 2. Oh, maybe I should have seen how to factor this. Ah, never mind. This factors into lambda minus 2, lambda plus 1. Actually, I should have known that because I made these problems, and more often than not I try to make the answers nice. So I'm trying to give you usually integer eigenvalues. Although you can see in a random situation you probably would get some very ugly eigenvalues. Okay, so I've got two eigenvalues, lambda equals 2 and lambda equals -1. Now, this is like the best situation you can possibly be in. Two distinct real eigenvalues. When you have distinct eigenvalues, actually due to some theory in linear algebra, you'll be guaranteed to get enough linearly independent eigenvectors. So the fact that 2 is an eigenvalue tells us that there's going to be an eigenvector to go with it. The fact that -1 is an eigenvalue tells us that there will be an eigenvector to go with it. And the fact that the eigenvalues are distinct due to some linear algebra, some nice theory, ends up being enough to tell you that the two vectors you get in the end will be linearly independent. So once we see two distinct eigenvalues, we are very happy. We have high hopes for this problem. Okay, now find eigenvectors here. So what should I call an eigenvector? Let me look in your textbook and find the right notation so I'm being consistent. Looks like your textbook uses V, so I'm going to use that. And let's see, so V, let's say V has these two components, V sub x, V sub y. And it's going to be an eigenvector for this matrix with eigenvalue 2. I think when we were just doing pure linear algebra with no differential equations last time, I wasn't using V sub x, V sub y, I was maybe just calling these x and y. You can see here there would be some confusion if I just called these components of an eigenvector x and y, right? Since x and y are actually the names of these unknown functions. They're not constants. But these components of an eigenvector, these are going to be constants. Just some components of one constant vector that's related to this eigenvalue 2 in this constant matrix A. So that's why I'm using a slightly different notation. Okay, so to find eigenvectors, you need to find vectors that this matrix kills. And that comes down to finding... Oh, I'm sorry. You need to find vectors that this matrix here kills. So vectors of this matrix minus 2 times the identity kills. So it comes down to finding the null space of this matrix. 6, that's 8 minus 2 is 6. Minus 6, 9, and then -7 minus 2, that's minus 9. And the matrix is always going to be a singular matrix when you do this. That was the whole point of getting the determinant to be 0, right? So just find something non-zero in the null space of this. So focusing on one row is sufficient for that. So since I sort of did this, let me just skip to the one linear equation that you need to worry about. This. So Vx equals Vy, right? And so 1, 1 is in the null space. And if you have any doubt, you can check. Apply this matrix to 1, 1, and you should get 0, 0. Looks like that works. So here's our first eigenvalue-eigenvector pair. 2, 2 for an eigenvalue and 1, 1 for an eigenvector. Or any scalar multiple of 1, 1, but I like this way of writing 1, 1. Okay, let's do the same for lambda equals a -1. Now I'm interested in the null space of... Oh, actually, let me go. I can't even see the matrix anymore. So subtracting -1 off of the diagonal, I'm interested in the null space of 9, -6, 9, and then -6. So I've taken this and subtracted -1 off the diagonal. So what's the null space of this matrix? So if my eigenvector, again, is called Vx, Vy, then I just need one of the linear equations I get out of trying to find the null space. So 9Vx minus 6Vy equals 0. That's sufficient to look at. Divide everything by 3, because we can. 3Vx, and move this to the other side, equals 2Vy. So what's a good vector Vx, Vy that satisfies this equation. So I could go ahead and solve for one in terms of the other, then I'll get either a 3/2 somewhere or a 2/3 somewhere, depending on which one I solve for. But I could also avoid fractions altogether by finding the following solution. If you choose 2 for Vx and 3 for Vy, then that solves it, right? And one solution is enough. So 2, 3, I think will be an eigenvector. And if I'm not sure, then I can apply this matrix to this vector and make sure I get 0. And just eyeballing it, that looks like it works. So there's our second eigenvalue-eigenvector pair. It's this and this. And as I promised earlier, these did end up being linearly independent. Alright, so how does this lead to a solution to the differential equation? Well, here comes that principle from earlier. This is the most important fact in chapter 4, that if you have an eigenvector for a matrix with a certain eigenvalue, then create this function like this, e to the eigenvalue times time times eigenvector, and that will be a solution to your differential equation with the matrix A as the matrix of coefficients. So we're just going to build these now. So if I create this construction with the first eigenvalue-eigenvector pair that I got, 2 and 1, 1, then I get, let's call it x1 of t equals e to the 2t times 1, 1. And when I do the construction with the second pair, I get x2 of t, let's call it, equals e to the minus t times 2, 3. And look at that. Here are my two linearly independent solutions. I can now write down a general solution. So let me copy those over to a clean page. All right, here they are, and here's my general solution then. It'll be C1 times this. And by the way, oh, did I forget the vector symbols back there? Yes, I did. These are not x's, they're xy packages together, right? So my general solution is this plus C2 times the other one. So there it is. And now I've successfully completed part A. I hope it came out right. I guess we'll find out in the later parts if there was a mistake somewhere. Okay, well, let's say you started, we started the whole story with this, right? So we had two unknown functions, x of t and y of t. Have we actually found what those functions are? Have we found solutions for x of t, y of t? What's all this vector nonsense? Where's my original x of t and y of t ordinary functions that I was looking for? Well, they're still here. This is actually just writing, this equality is an equality of vector objects, right? So it's just really two equations packaged into one. So if I write the left-hand side out as what it is, and combine, this combination of vectors is a vector, right? If I just carry it out, stick the scalars inside, actually carry out the scaling, and actually add the vectors, it just adds the components, then you're looking at this times 1 plus c2 e to the minus t times 2. Let me stick the 2 in front there. And then c1 e to the 2t times 1 plus c2 e to the minus t times 3. And then what we're writing down here is just this. It's an equality of two lists each of two things. So what that means is, when we say these two lists are equal, what that means is each component is equal to each corresponding component. So I can erase the brackets and then put two equal signs, and that's the same thing. So there's what we were ultimately after. But notice I did not write it like that until I reached the end, right? I keep everything packaged together so I can do my linear algebra until I reach the end. At the very end, then I get this. And now you can see what I meant by keeping things packaged together makes it clear how to treat the constants in front. This has two constants in front, and so does this, but they're related, right? Like the C1 showing up here is the very same C1 that's showing up here, and the C2 here is the C2 here. So it's not like you have 4 unknown free parameters here. You still only have 2. It's just that they're linked in a certain way. So apparently the way they're linked here is that the free parameter, or the coefficient in front of e to the 2t in x equals the coefficient in front of e to the 2t in y. And apparently the coefficient in front of e to the 2t in x is, I guess it's 2/3 times the coefficient in front of e to the minus t in y. So they are linked. Now I'm going to actually get this out of my face for a bit, this whole thing here, if I can grab it. What I'll really consider to be the most useful form for the general solution is this. And I would recommend, to the extent that you can, do your calculations with this. When you go to do part C, satisfying certain initial conditions, you will actually be asked for separate functions x of t and y of t. Then you can go separate things like I was doing. But until you reach this last phase where you're inputting the final answer, I would say keep everything packaged together. Okay, now I kind of want to do part B, way the end without a computer. So what we're looking at here is a 2-parameter family of solutions. So the 2 parameters are C1 and C2. So if you pick 2 numbers, C1 and C2, then this will give you some trajectory in the phase plane. And what do those trajectories look like? Can we get a feel for what they look like? It's kind of a difficult question at first, right? Because it's not like one trajectory. It's a 2-parameter family of trajectories. So given any initial condition, which requires specifying 2 values, the x and initial y. So given any initial condition, there will be a trajectory passing through there. So what we expect is like some entire family of trajectories filling the space, filling the phase plane. And somehow these all have some shape and some way that they're related to each other. So it's not just asking what one trajectory looks like, but what does the family of trajectories look like? Well, here's a way of starting to answer this question. Try C1 equals 1 and C2 equals 0, and also try the opposite. So in other words, try the eigensolutions themselves, if you want to call these eigensolutions. Try these original ones we constructed before we took linear combinations. These are solutions, and they're part of this family, right? They're what you get when you put in 1 for C1 and 0 for C2, or vice versa. So let's start with these specific trajectories. What do these look like? So let's do this one in green. What does it look like? Well, at any given time, it's going to give us some, at any given time t, it's going to give us some point in here, right? And then as I play time forward, I'll see that point move around, and that will be like an animation, and it'll trace out some kind of curve or some kind of line. Now, notice the eigenvector is just a vector of constants, right? And then all that's changing as I vary time is the scalar in front. So what shape does this trace out? It's just a line, right? At time 0, it starts at e to the 0, so that's 1. It starts at 1, 1. So let's say here's 1, 1. At time 0, it's at 1, 1. I think that's closer to 1, 1 maybe. I don't know. 1 over 1 up. So it starts there. And then as you increase time, what happens? As you play time forward, where does this dot go? It just scales out away from the origin, right? It's just multiplying this vector by larger and larger scalars. And, it might start moving more slowly, but then it accelerates very quickly, right? It takes off exponentially the scalar in front grows exponentially. So that's what you see if you only consider from time equals 0 to, various positive times. Then you see this. And I'm putting the arrow there to indicate which way is the future, which way the dot moves as you play the animation. But we can also allow negative time, by which I mean look at what was happening in the past, before time 0, and what happens when you consider more and more negative values of t as you look further and further into the past for this trajectory. Well, you see that the dot came from ever closer and closer to the origin, right? As t becomes more and more negative, e to the 2t becomes closer and closer to 0, right? If I just plot against t, e to the 2t, it looks like this. As t gets positive, it blows up. As t gets more and more negative, it asymptotically goes towards 0. So as t gets more and more negative, the scalar in front of the vector 1, 1 is getting closer and closer to 0. As you look deeper into the past, you see that this trajectory was closer and closer to 0 at different times, but it never was at 0, because this scalar never reaches 0. So x is always a positive scalar times 1, 1. So this is the full picture here, and maybe I can put this dot here to indicate that's where time 0 was. This is the full picture of x1 of t. Actually, let me leave that picture up there. Let's do x2 of t. How about we do that one in blue? So again, at time 0, it's located at the vector 2, 3, right? Because when I put in 0, this coefficient is 1. And where's 2, 3? So maybe over here, let's say it's over here. Let me exaggerate a little bit and say it's over here. So you'll see how that later makes the picture easier to draw. Then what happens as I increase time? Actually, as I increase time, that scalar in front decays, right? This is what's happening. So if I were to plot e to the negative t against t, in the future, this is exponential decay. So in the future, it decays towards 0, and in the past, it was sort of blowing up exponentially. So now this arrow is like this, indicating that this is the future direction. If you put the dot here and then you play time forward, it's going to go down towards the origin. And you've always got a scalar multiple of 2, 3. So that's why it's going along a straight line. So there's your two eigensolutions. Oh, you can also look in the past for this one. In the past, it came from up there, right? So there's your two eigensolutions. And these sort of tell you about what's going on with all of the initial conditions that sit on these lines. So if your initial conditions are just perfect, so that they sit on these lines, if your initial x and initial y sit on one of these lines, then the behavior in time is going to be very simple, is that x and y just travel along a line, and they always have the same proportion to one another. So one way you can think about what's going on here is that x is always equal to y. They have maybe a complicated relationship with time, thanks to the exponential showing up here. They're like exponentially growing or exponentially decaying for the blue one. But here, x and y are always equal. Here, x and y are always in a sort of 2/3 or 3/2, whatever you want to call it, proportion to each other. So the relationship between x and y is very simple. That's if you have perfect initial conditions and start on one of these lines. If your initial conditions are not so perfect, and they're in just some random place, like start here, or start here, or start here, or start here, then what's going to happen? Then you'll get some interesting curvy trajectory, who knows what. Actually, we can draw that into our picture. There are techniques for doing this, which I'm going to show. First, I want to extend these lines. And the reason I'm doing this is that they're actually more than just starting along this ray here. even if I'm not starting exactly along this ray, there are some other points where I will still travel along a straight line if I start there, and that's the points down here. Those correspond to if I chose, so the points down here correspond to choosing C2 being -1 and C1 being 0. Then I would be looking at the negative of x2. So this blue ray here is like x2 of t is that trajectory, and then this blue ray is the negative of x2 of t. And this green ray is x1 of t, negative x1 of t. So this, the reason to draw the full lines here is because these lines end up actually dividing the plane into four regions. So this region, this region, this region, and this region. And you'll get different behaviors depending on whether your initial conditions are in one or the other of these four regions. Let me fill in the arrows here. So the blue solutions always go towards 0, because as you increase time, the scalar in front decays. Whether you put a plus sign or a minus sign in front, that's the case. The scalar in front decays. And the green solutions always explode out away from the origin, because as you increase time, the scalar in front explodes, and it either explodes positively or negatively. Either way, it explodes. So both of these are just going to go away from the origin. Let me get this out of the way. Okay, so far we've looked at only the special cases, right? These two special cases, or four special cases if you include the negative ones versions. But what about the general case? So let's use the color red for that. So what about if my initial condition is not on these lines, if it starts here somewhere or here somewhere, then what happens? Oh, I'm not sure if that was recording what I just said, so either I'm repeating myself or saying it for the first time. So what we looked at just now are two special cases, the green and the blue special cases. And now I'd like to look at the general case. What if our initial conditions don't start quite on either of these lines, but they start either here or here or something like that? So I'm going to use red for that. All right, so it's pretty much the same way we were thinking about these. We were thinking about as time goes towards the future, as time goes forward, what happens in the long term? Does it explode away from the origin or go towards the origin? We're going to ask the same question here for the general situation. As time goes forward, what happens? It's just more complicated because there are two terms. But it's not that much more complicated because the two terms both involve exponential factors in front, and depending on whether you're looking towards the future or towards the past, since there are different exponential growth or decay rates, one or the other term will actually dominate the behavior. So like when you add two vectors, so this is like scalar times vector plus scalar times vector, right? If you linearly combine two vectors, then the vector you get will be, its direction will be a combination of these two directions, right? So the direction, if I draw a vector from the origin out to where x of t is, the direction of that will be a combination of the blue and the green directions. And the kind of combination I get, whether it's more pointing in the blue direction or more pointing in the green direction, that all depends on the size of the coefficients in front. Now look at what happens as t goes towards the future. So as t goes to positive infinity, so towards the distant future, what do you expect? This coefficient is decaying very quickly. It's exponential decay, right? And this coefficient is growing, and very quickly. It's exponential growth. So as t goes towards the future, definitely this dominates. So you're going to be pointing more in the blue direction as t goes towards the future. So let's express it like this. 1, direction is dominant. And what about when we look into the distant past? What direction used to be dominant? So in the distant past, as t becomes more and more negative, so imagine putting in like t equals negative 1 billion, then this term would be like e to the negative 1 billion. So it would be a very large. And this term would be e to a very negative number, so it would be very small. This would dominate, right? So then in the distant past, I would expect this, the green direction, is dominant. So what that amounts to in the picture is that the solution trajectories I draw, in the future direction they'll be parallel to blue, and in the past direction they'll be parallel to green. So that's good information, but I also don't even know exactly where to start my drawings. Where was a solution in the distant past? This tells me something about which direction it was probably going in the distant future or the distant past, but also where is it? So let me make some room for that kind of information. So it's going to be, let's see, so as I look towards the distant future, this basically becomes 0, right? This term can be dropped in the distant future. And this is the term that matters, at least as long as C1 is not 0. If C1 is 0, then I'm looking along the blue. And let's just ignore the blue since we already drew the solutions on the blue line, right? So let's just think about solutions off of the blue line. So C1 not 0. Then between these two terms, the first one definitely dominates in the future. The second one basically becomes nothing. So what happens as t goes to infinity? You actually approach the 1, 1 line. So, okay, these look almost like they're saying the same thing, but I am trying to say different things here. Here I'm trying to say that in the future you approach the actual green line. You approach the green line. And in this first fact, I'm trying to say that you approach, your direction becomes parallel to the green line also. So both of those happen. Here, what are you going to approach as you look in the distant past? You actually approach the blue line. So you approach 2, 3 with similar kind of reasoning. Okay, let's get to drawing this. So how about I go past to future? So in the past, the 2, 3 direction was dominant, and I'm approaching 2, 3. So that's the blue direction. Wait, then why did I make it in green? Not sure what I was thinking there. I think I wrote the correct vector, but I wrote it in the wrong color. I'm really sorry. That's incredibly confusing. Okay, there we go. So in the past, we're coming in from the blue direction. And we're coming in parallel to the blue direction. So we expect trajectories to come in like this and from this direction. Oh yeah, and I said I would make these trajectories in red. So we expect trajectories to come in like this and in this direction. So that's the past shape of a general trajectory. And then in the future, I expect more parallel to green and in the green direction. So how do I connect these up? You can do this, and this is what it turns out happens. So this is what the trajectories look like. Different things in this family, where the reasoning here is telling us the asymptotic behavior, that in the past they're coming in parallel to blue and from along the blue line, and in the future they're going parallel to green and along the green line. And you can do the same for the others. So here's past. For the other quadrants, I mean, here's future. How would you connect these? Like that. Same thing here, past, future. You can connect them like that. And then here, past, future. So you can see how these blue and green lines separated the plane into 4 quadrants where you get different families in between them. So because they separate the plane like this, these lines, the blue and green lines, are called separatrix. Each one is called a separatrix, and together they're called separatrices. So of course the origin itself is very special throughout all this, because it's a critical point, right? Our original differential equation is autonomous. Is x prime equals ax. This is autonomous with a critical point being 0, the only critical point being 0 in this case. So solutions that start at the origin just stay at the origin forever. That corresponds to C1 and C2 both being chosen to be 0. All right, I'm going to try this a little bit in Mathematica and just see if I can get a picture that looks like this, and maybe with some animations. So here's how I'm typing in my general solution, like this, with some coefficients C1 and C2. So definitely I cannot plot this. If I try to parametric plot it, it should not work, because it doesn't know what are C1 and C2. Let's say I do from t equals 0 to 5 or something. There's nothing to plot yet. But if I pick specific values for C1 and C2, like here's a way of just saying plot it with the assumption that C1 is 1 and C2 is 0. Then I get this line, and the plot range is very large because of the exponential growth here, e to the 2t. Maybe if I ran it for shorter time, it would look more reasonable. Yeah, so what we're seeing here is this green ray. Let me just type in a plot range here. Yeah, so you can see it's this green ray, and it starts from 1, 1. I could start it from including negative time a little bit like that. So now it looks like it's starting from the origin, but of course it actually is just starting from very close to the origin. Okay, now instead of putting in C1 and C2 specifically like this, let's not choose what they are, and instead let's do a table that shows a bunch of these trajectories. So table, it doesn't actually mean table. In Mathematica it means make a list of these. So let's make our list do different values of C1. How about ranging from negative 2 to 2 with a step size of 0.5. So like negative 2, negative 1.5, negative 1, and so on, all the way up to 2. And then I'll do the same thing for C2. And if you want to do this in, say, Desmos, you can just manually put in a bunch of functions like these with different values of C1 and C2 chosen. Or actually, you can even make a little slider bar for C1 and C2 and watch what happens as you slide them around. Okay, so this is our bunch of trajectories. So that looks pretty cool, but I want to see them all in the same plot rather than seeing a list of plots. So let's show. And there's that picture. It just doesn't look as good, but it is that picture. Let me play with the plot range a little bit off screen and see if I can make it look better. Okay, maybe that's a little better. I don't know, but you can see that it's this. Okay, how about we get an animation going also? Okay, here's the command I would use to show a point at the origin, and I can put whatever coordinates I want here. So I want to use x of t, the solution function that I got as my coordinates. So for example, maybe x of 0, but that's not so good, because I need to decide what are C1 and C2. So let's make C1 be 1 and C2 be 0. Now it'll always look centered unless I add some more options. Okay, that's looking better. Now there's a dot there, and if I put time 0, then I get this, but then at time like 0.5, the dot moves, and at time 1, the dot moves even more. And this is C1 equals 0, C1 equals 1, C2 equals 0. So that's this term only, this term being dropped. That's the green line. So the dot is actually traveling up the green line there. And I can make this an animation, so put a parameter here, t, and then animate. And t is what's playing in the animation. So t is going to change from 0 continuously to like 3. And you can watch the dot travel up the green line here. Okay, but let's do a more interesting one. How about one of these curvy red trajectories? So one problem is right now I don't have much control over where the dot starts, right? I can choose what are C1 and C2, but that determines where the dot starts, but I am not very clear on exactly how it determines that. So what I need to do is solve the full initial value problem. So here I've got my general solution, but I haven't solved the full initial value problem. So how about we solve this specific initial value problem that's being asked in part C here. So find the solution that satisfies these initial conditions. Once I figure out that solution, then I can plot it and watch the dot move around and see the animation, but I can already make a prediction as to what's going to happen. If I start at 1, 0 here, then I'm starting on the x-axis. So I predict I'm just going to fly out in a slightly curved trajectory like that along one of these red lines. Actually, I'll fly up and eventually I'll be parallel to the green, like that. Okay, this video is running way too long, I think, so let me do the initial conditions in the next video.